Okay, here's another example of a separable differential equation. Question 22, page 49. Here's the differential equation, and we're given an initial condition. That's not that hard to solve. Separating it is easy. Integrating both sides is easy also. Using the initial condition, that if x is 1, y is 0, that's easy to use. You'll get that constant is -1, and so you'll get an implicit particular solution. It's implicit because I haven't explicitly expressed it to be y as a function of x. Okay, that part with 22, that's not so hard to do. What's a little bit hard to think about is to give the interval on which the solution is defined. Okay, so think of it like this. Here's a sample implicit curve, and this is, I think, fairly close to what this particular solution actually looks like. Okay, I'll show you why in a minute. There's a few things about this. There might be a portion on the curve that contains our initial condition, and we might think that if it's not an explicit function, then it might, or it'd have to overlap itself somehow. So imagine this on the xy plane. This single value of x would give you, say, 1, 2, 3 different values of y. Now, if you take only that portion of it, or if you take only this portion of it, well, those would be explicit functions of x, but the whole thing isn't. Now, what separates them? How does it make the transition from one explicit function to another? The key there is the vertical tangents. If it's going to overlap itself, you think it'd have to do something like that. Okay. So let's see. About the vertical tangents, what's that mean in terms of slope? Well, if it's vertical, the slope's undefined. That means dy dx is undefined. Okay? And then the solution, whatever the solution is to this, is not defined if there's a vertical tangent, because you have a differential equation and it involves dy dx. Okay? I meant to write dx there. It involves the derivative, and that's what a differential equation is, an equation that involves the derivatives of some unknown function. Okay, well, we can't have that be undefined, because then you wouldn't have a solution to this, whatever the differential equation is. So if we can give the interval where that's defined, if we find out where the vertical tangents are, okay? Now, this original differential equation expressed something about the slope of this implicit particular solution. It says dy dx has to be like so. What would it take for that expression to be undefined? Well, whenever, I suppose, 3y squared minus 4 is equal to 0. Okay, so let's do this. So here is how dy dx varies with y. So what's it going to take to make 3y squared minus 4 0? Just set it equal to 0 and solve it. You'll get 2 over root 3 and -2 over root 3. And it's undefined. I'm going to write that, okay? And all I'm saying is that the slope dy dx, the slope of the solution, is going to be vertical at those places. If I would do a little bit more math, I can tell that 3x squared is always positive. There's no way that's going to be negative. But this 3y squared minus 4 will be minus here and plus here and there. So at this point, it's almost like I can envision something like a direction field. Okay? So here's the xy plane. And I'm going to put, this is just a reference line. I'm not saying the slope's flat or 0 there. That's just for reference. This is y is equal to 2 over root 3. It's going to be vertical. And then at this mere reference below it, y is equal to negative 2 over root 3, it's also vertical. Okay, where's our initial condition? Initial condition, if x is 1, y is 0, the initial condition is right here. So it's got to have a slope that's falling, and then it's vertical, and then when you go below that, it's rising. So it makes me think that somehow it's, this is sort of what I envision, like something kind of like that. Vertical right there, transitioning to falling, vertical, and transitioning to rising. So, okay, now I guess I want, like I'm trying to extract this part of the curve. I want to tell you the x's that will put you on that part. That'll be the interval on which the solution is defined. Okay, well, I guess you would just want the x to keep you between this y value and that one. Okay, because we're envisioning something like this. So just find the x that takes you here and find the x that takes you there, and you want to be in between. All right. Okay, so about how would you do that? Well, so this is our solution curve, right? This is the xy plane where this solution curve exists. That's how its slope varies. Here's the initial condition. We would just in that take, let's start with this one, 2 over root 3. Okay, let's let y be 2 over root 3 and see what that means for x. So if I do that in here, I'll get 8 over 3 root 3, okay, minus, what's that going to be? 8 over root 3. Okay, and then equals x to the third power minus 1. So that's allowing me to find, what that number is. Okay, all right. So do a little math here to figure that out. So that's going to be a 24. So minus 16 over 3 root 3 is x to the third power minus 1. And I want to tell you the x, so I add 1. And it's going to look like this, 3 root 3 minus 16 over 3 root 3. And that would be me moving the 1 over and getting a common denominator and all that. And I guess to finally solve for the x, I would be doing that. Okay? All right. Yeah, so that's how it would go. Now, if you put this in your calculator, of course, nobody's going to do that in their head. It's going to be negative 1.28, say if we round to 2 decimal places. So that's where this is. That's the x coordinate that takes you to that vertical tangent. Now, from here, what you do is you put this one in also, put it into that, and tell me the x, because we're trying to figure out some restriction on the solution curve that's going to pick this part out of it. And here's what you'll get, all right? We'll say, here's my implicit particular solution, and you want to keep it on the interval negative 1.28 less than x, less than, and that number that you're going to get from the other one is about 1.598. All right. Okay, so we'll put it on that interval. And all that does is identify this part of it. So here's my implicit particular solution and the interval on which it's defined for that original differential equation.